So today's topic is slope fields. So these are kind of weird things. You've seen them before, believe it or not. You probably didn't recognize them, but these are situations where we have a differential equation that is neither separable nor solvable by analytic methods. So in other words, by our algebra skills, we can't separate it and get dy on one side and dx stuff on the other side. So this is a method that we can use to still find general and particular solutions, but we do it graphically. So this is all done graphically. We have a picture of those solutions as opposed to a actual equation. So definition, a slope field, I'll highlight that. A slope field is a general solution. The particular solution in the slope field is a continuous function that passes through some initial conditions. So like f of 0 equals 4 or something like that. So yet again, the slope field is a general solution, but it's a graphical general solution. So, okay, so we've got this idea that a derivative finds slopes. So we've got, this is the equation for all the derivatives. So dy dx is equal to x squared. Now this is one that you could solve, you could separate and solve, all right? But the way you want to think about it is this idea that all these derivatives are all the slopes of the original functions x and y's. So let's look at a picture of a slope field. So here's a picture, like I said, you've probably seen this before on a what? This is a weather map. This is the wind, the high pressure system and low pressure systems coming in. Those are just slope fields that your computer, that the weather person's computer could generate. And so the idea that our solutions, our general solutions, are, you can only do it if the curves don't intersect. And this one, they all kind of go together. But the ones we're going to look at always come out real nice. So this is what we would call a slope field. He says that they're called vector fields. I've never heard that before. Flow field kind of makes sense because it's the way that the function flows as we move around. So there's the kind of initial idea. Let's talk about a little bit more about what slope fields are mathematically, then we'll get into some examples that'll make more sense. So if we have the differential equation y is equal to dy dx, every point of our original, of the function that we're trying to graph, okay, the graph of f, you're going to assign a small piece of a tangent line with a slope, okay, with that slope dy dx. You'll see what I'm talking about. Let's just jump down there and get into it right away. So here's our dy dx. Now we could do this algebraically, and we will in a minute to see what the curve looks like. But let's try to sketch the slope field first. So what I want to do is I want to assign a small piece, a small tangent line with the slope at a certain x and y value. So for instance, what is this x and y value? This is the point 0, 0. So you would take 0, 0 and you would plug it in to dy dx equals x squared. Well, there is no y to plug it into, so basically we're just plugging x into this thing. So when we plug x into this thing, we get 0. 0 squared is 0. So at 0, 0, our function is going to have a slope of 0. Let's go to the next point that makes sense, which would be 0, 1. Well, at 0, 1, again, we're only plugging in x values, so we're only plugging in the 0 again. 0 squared is 0. So I'm drawing a little bit of a tangent line. And now I'm going to kind of go quick here because all of these have x values that are 0. Then let's move over. When we graph these folks at the indicated points, this is almost always referring to the lattice points. You don't want to do this. It'd be impossible. The lattice points are the intersection points. So like when you have the grid, it's where the horizontal and vertical lines intersect each other. You don't want to graph this for all of them. And usually, I guess I shouldn't say usually, sometimes they'll say at the 8 indicated points or at the 4 indicated points, and they'll give you a specific amount of points. So we figured out at these x values, let's figure out as we move here. This is the x value 1, the y value 0, but yet again, we don't care about the y value in this case. So our slope is 1. My tangent line would have a slope of 1. Now I'm going to be picky about the ones that should be a slope of 0 and the slope of 1. Everything after that, as long as you're close, we let it slide. Okay, so this also has an x value of 1, x value of 1, x value of 1, x value of 1. Those should be at 45-degree angles because the line y equals x is, just that 45-degree angle line. Let's go to these. Now this is a slope of 2. Well, how exactly are you going to figure out a slope of 2? Like I said, I'm not going to be super picky. Try to make it a little bit steeper than the slope that you did at 1. All right, moving over here, what's our x value? Our x value is -1. Plug it in. We get another slope of 1. These I'm going to be picky about. These should be right at a 45. And notice I don't make the tangent lines too big. You can make them bigger if you want to, but you really got to make sure that they don't get into messing with the next tangent line. You don't want these things to intersect each other. And then we got our -2, which is going to give us I said a 2 over here. I meant a 4. Sorry. That's 2. 2 squared is 4. So my slope at 4, I don't know, something like that. I'm just going to try to make it steeper than the slope before it. All right, that's your answer. This is what we would call, this is the general solution, a slope field. Why did I write that? Slope field is the general solution. So we have a bunch of different curves in here. We have a bunch of different functions in here. They're all amended by this plus c, the plus c that we would usually get by solving the differential equation. These are all different graphs that are all amended depending on where you start. So let's pick some random place to start. I'm going to pick the spot. I'm going to use the one that Corpy used, which is -2, 0. Sorry, -2, -1. So -2, -1. That's my initial condition. So what I'm going to do now is I'm going to try to sketch it. I'm not very good at this, and so it's going to take you probably some time too. Maybe not. Maybe you see this better than I do. What I'm going to try to do is I'm going to try to draw, so this slope kind of came out like that. Okay, these slopes go down to 1. Then this goes down to 0. Okay, this slope there is 0. And then the slopes start going up again. There's a slope of 1. Then the slopes start getting steeper, slopes of 2, and so on and so on and so on. And then kind of going backwards, these have a slope. There's my function. Now, does that fit with what we would expect? I hope it would, considering that if our derivative is x squared, what's our original function? Integrate x squared. You could probably do that in your head. You get an idea of what this graph looks like. But let's find it specifically. Let's just review what we did yesterday. Or sorry, not yesterday, but last time. So last time we took this and we tried to solve this, doing separation of my variables. So I'm going to move dx to the other side, so I get dy equals x squared dx. Now I'm going to integrate. What's the integral of dy? Well, that's y. The integral of x squared is x cubed over 3 plus c. What's our initial condition? I told you that we're starting at a specific spot, so our initial condition was the point -2, -1. So let's see what c, the actual value for c would be. So I'd plug in -1 for y, plug in -2 for x. -1 equals, that'd be -8/3 plus c, add that over. So that'd be what, -3/3 plus 8/3 would be 5/3. And so we would have y equals x cubed over 3 plus 5/3. Does that seem like a reasonable? Yeah, I'd say that's pretty close, right? I mean, my y-intercept certainly wasn't very good. 5/3 would be a little bit bigger than, well, quite a bit bigger. It'd be 1 2/3. So my graph, look, that's what I'm not going to be super picky about this. Not going to be super picky. It just has to look reasonably well into the slope field. What you must hit, must use initial condition. So you must hit that point. There's no excuse for not missing, or there's no excuse for missing that point. But everything after that, as long as it looks decent, I'll call it good. And another thing when I'm talking about my slopes, I'm not going to be super picky. Well, I'll talk about that in the next section. So this, I want to leave myself a little note here. This would be the particular solution with the initial condition of -2, -1. The general solution are all those different pink graphs. Now you could imagine if I started up here, or let's say I started over here, my graph would still look basically like a cubic, but it would have a different height. It would have a different vertical shift. So a couple of notes, a couple of things that are important. When drawing a piece of the tangent line at the point, you must draw the line long enough to see, but not so long it interferes with other ones. So draw it, but don't draw it super long. The second note, your slopes of 0, 1, -1, and infinity are expected to be spot on. They should be perfectly, 1 is a positive 45 degrees, -1 is a negative 45 degrees. 0, slope of 0 is horizontal, slope of infinity is vertical. All the other slopes are going to be done relative to these slopes. So whatever 45 degrees, once you draw that, your slope of 2 just needs to be steeper than that slope of 1. And then when drawing a particular solution, you must have a continuous functional curve, and it has to pass through the given point. So you must hit that, the given y value, like I said in that last example. So this is his drawing. He, if you open up his PDF or my PDF of his work, you get a better picture of this. But this is why we use a computer most of the time to do a slope field. Could you imagine doing this slope field? I mean, what is there? 100, probably 100 points in there, 100 lattice points that we'd have to plug and chug and figure out. So our computer does a really nice job of this. And like I said, you see it every night on the nightly the nightly news during the weather segment. But this is the graph that we did on the front, the slope field that we did on the front to a larger scale, with better details. All right, so sketch the graph of the non-separable initial with the initial value problems. All right, so here's our function. Now this would look like, let's just prove that this thing, we couldn't solve this algebraically. So this is basically saying dy dx equals x plus y. Well, I want to get all the y stuff on one side and the dx stuff on the other side, but I can't have it both ways. I can't multiply by dx and then subtract y because I'd have to distribute the dx. Well, let's move the y first then. So I would get dy dx minus y equals x. Well, now I times by dx to move it over here. Yeah, I got a dx there, but I'd have to distribute it, and I'd still have a dx here. So there's no way for me to separate this so that I can use my algebra skills to actually integrate. So this is where our slope field really comes into play. Let's see if you can do it on your own. See if you can figure it. Well, this one's kind of crappy because he made the block so big. But anyway, try to do the best you can on drawing this slope field. Pause it if you haven't yet. Okay, let's see how you did. So I would take this point and I would plug it into my derivative function. So this is the point 0, 0. So what's 0 plus 0 is 0. I got to kind of draw it big. I want to draw that perfectly horizontal. Then you could pick whatever points. Usually you kind of try to find a pattern. And once you get to see the pattern, then you can go a little bit quicker. But okay, so this is a 1 for an X and a 0 for a Y. So when I plug in 1 plus 0, that's 1. I need to draw this thing at a 45-degree angle. This is 2 and 0. 2 plus 0 is 2. So I'm going to try to draw that a little bit steeper. This is negative 1 and 0, which would be negative 1. Didn't draw that one very well. That would be negative 2. Try to draw it a little bit steeper. Okay, let's jump up to this one. That is 0, 1, so that's also 1. This is negative 1, 1. Negative 1 plus 1 is 0. Maybe there's a pattern here, huh? Let's see if this is negative 1. So that's negative 2 plus 1 is negative 1, yeah. I'm guessing this is going to be negative 1. 0 plus negative 1 is negative 1. I'm guessing this is 0. Right, 1 and negative 1. This is 2 and negative 1, so that's 1. This is 1 and 1, so that's 2. Oh boy, this is 2 and 1, so that's 3. It's going to look basically horizontal, or even try to make it look a little steeper. I'm going to give you, like I said, lots of leeway. Negative 1 and 1. Oh, wait. Negative 1 and negative 1 is negative 2. Negative 2 and negative 1 is negative 3. So something like that. So there's my slope field. That's the general solution. Then they would like us to sketch the particular solutions given some initial condition. So this is y of 0 equals 1. So at 0, 1, I must hit that point. So I'm going to highlight that with a big, you can barely see it, but make sure that you actually hit that point, 0, 1. Okay, let's see. So the slope here is basically straight. I'm going to go only one direction first. So I'm going to go down like this. And then it looks like, remember, through here, all these slopes should be 0. So I should level off there. And then what are these slopes here? These slopes are always getting closer and closer to 1. So my graph is going to look something like this on this side. And then these slopes just getting bigger and bigger and bigger. So it looks something like that. So this is the graph of A. All right, let's try the graph of B. So I'm at negative 1.5, negative 0.5, so that's here. This is the point, negative 1.5, negative 0.5. Okay, so let's see. So my slopes are kind of steep going this way. And then they kind of go down, they kind of go to a 45-degree angle. And remember, this one just kept getting steeper and steeper and steeper. This came 3 and then 4, and then it's going to look something like that. Oh boy. Like I said, if you're close, I'm going to give it to you. I struggle with this. I struggle with this drawing. Negative 1, 0. Negative 1, 0. Okay, that's here. Make sure that you at least hit that 1 point. Okay, the slope goes out at a 45, then the next one's at a 45, and the next one's at a 40. Well, this one's pretty, I like that one. Negative 1, 0. That's the graph of C. So I don't know if you caught this, but this is an example. You remember doing slant essays, slant asymptotes when we did our rational functions back in the day? This is an example of a rational function. So just as a reminder, this is an example of a rational function, but with a slant asymptote. Just as a reminder, you must hit these givens. Those are the only points that I'm going to really be picky about. From there, I'll give you some leeway. All right, yeah, let's have you do this one. You don't need me. So sketch the slope field given that differential equation. Pause it if you haven't yet. All right, let's see how you did. So this would be 0, 0, 0, 0, and -1 would be -1. This should be at a 45. This is 1, 0, so that's a 1, that's a 0, so that's 0. Ugh, I hate that. Gotta draw those so weird. That's horizontal. Let's go to this one next, I guess. -1. Yeah, that's still horizontal, isn't it? Because it's -1 squared, which is 1. That's 0. 1 minus 1 is 0. This is 0, 1. So that's 0. That's 1. So this now is horizontal again. Let's go down to this one. That's 0. That's -1, but that's 1 when I square it. 1, 1. That'd be 1 plus 1. Take away 1 is 1. That's -1, which is 1, and 1, which is 2. Take away 1, which is 1. Man, I can fill out the slope field really well. I'm already thinking ahead of sketching the solution, and I struggle with that part. -1 and 1, that'd be 1, 1, that'd be 1 again. This would be 1 again. Good night. What does that look like? Well, I guess there's some similarities, right? So these are some places where the slopes are horizontal. So I should be leveling off when I go through those areas. Let's see if this helps. Okay, let's give it a try. Sketch the solution that goes through the origin. Highlight that point. At least get your 1 point there. And then I'm going to give you a second to try to sketch. All right, let's see how you did. So as you come out here, when I get to this spot, kind of like those are all horizontal, so that means these horizontals probably go like this. I can make that prediction. So I should level off. And as I go further out, it's going to come back down, something like that. And then over here, this one definitely goes out at a 45. And then here's my horizontals again. So when I get in that zone, I'm going to level off. And then I'm going to go back up, something like this, I guess. I don't know. Close enough? That would be a good enough. This would be the particular solution. Particular solution through 0, 0. And then in pink is the general solution. So like we talked about it earlier, the computer does a much nicer job of this. So Corpy printed for us a picture of this slope field on a computer. And then he had the computer do some particular solutions. Now this is a little bit misleading to what we had because ours only goes to 1 where his goes to 3. But look, if we chop down to 1 here, we didn't do too bad. We didn't do too bad, right? That curve that goes through the origin. That was pretty much what we did up there. So slope fields, particular slope fields are pretty much an exact science. Actually, how about this? They're an exact science for every slope that's 0 or 1 or -1 or infinity. Everything else is kind of a decent estimate. And then when you draw the particular solution, it's really just an estimate as best you can. All right, here we go again. I'm going to encourage you to pause. Notice it says at the 8 indicated points. So this is this happens a lot where they tell us this happens a lot where you only have to do it at the 8 points. So don't do it everywhere, just at the 8 points that they indicated. All right, hopefully you paused and gave it a whirl. So this would be 1, 1, 0. That would be 1. That would be 0. That would be 2. Ugh, I hate drawing 2 before I draw 1. Okay, I got to make it steeper than a 45. There we go. Close enough. That's 1, 1. So that would be 3 over 1. So that's even steeper. I'm not doing a very good job on making my picks here. This is 1, -1. So that would be 1 for x, -1. So there's our 1 finally. This would be 2, 0. That would also be 1. -1, 0 would be -2. Draw it fairly steep, or try to. -1, 1, that would be -3. Steeper. negative 1, that'd be 1 over, that'd be negative 1, so that's a nice one, 45 degrees. Negative 2 and 0, that would just be negative 1 again, so I'd negative 45 degrees. So all these are going to be negative, these are all going to be slopes of 1. All right, let's try to sketch this thing. So there's our general solution. There's our, now sketch a solution, a particular solution. Solution curve is a particular solution. And so we're going to start at 1, 1. Make sure you hit that point. Okay, that one's easy to start off with. Let's go this way first. Okay, there, something like that maybe. Actually, it probably goes something like this, doesn't it? Because those slopes are going to get closer to, whatever. Now, as I come in here, remember, we've got to be a little bit careful. So when I get to this spot, don't forget, they told us off the bat that the derivatives, that the slopes do not exist at 0. So when I get to this spot, there's two things that are going to happen. I'm either going to have a hole or, and I'm not so sure that it doesn't do this either, maybe it makes an asymptote there. In either case, let's go back a couple of pages. Flip back to page 3. What's one of the definitions of a particular solution? A continuous functional curve that goes through the given point. So we can stop right now. There is no particular solution in this case. So I'm going to change my color. No solution curve because dy dx equals dne if x equals 0. So we have a discontinuity. So we have some discontinuity that we can't finish our solution curve because x equals 0 doesn't exist. All right, these are kind of fun. This is where we would look at the curve and try to match it to the function. And some of these are easier than others. Now remember, this is the picture of the original curve. So it's all their slopes. So there's a couple of different ways that you can do this. You can kind of try to plug and chug. Like for instance, at the point 0, 0, we have a slope of 1, right? That definitely looks like a 1. So I can try to plug in to these values and try to see which ones have an answer of 1. That's one option. The other option is just to look at it and try to make a guess on what you think what a particular solution would be. So like this one, if I were to sketch a particular solution, I would say it looks something like that. Do we have any curves that look like that? Of course, right? This is one of our sine or cosine curves. Now they're sneaky. They're going to give us both of them in here. So we got to do a little bit of thinking. Is this a picture of sine or is this a picture of cosine? Pause it if you can't. If you don't know, I'm sad. Try to pause it and figure it out. Okay, here's how I looked at it. I looked at this as being degree 0 or 0 radians. At 0 radians, so on the unit circle, over here at 0, that's the point 1 comma 0. So which one, sine or cosine, has the y value of 0? It's sine. So this is the F curve. All right, let's try it again for the next one. I like doing the particular solution thing. So it's going to look something like that. Looking at my functions, is that a horizontal line? No. Is that the identity line? No. Is that a parabola? No. Is that a cubic? Yes. Could be. Is it a rational or reciprocal squared? No. Is it a trig? Trig? No. Is it a natural log? No. So this is definitely going to be E. No, sorry, D. Now we would have some problems if they put tangent. What if they put tangent as an option? Oof, that could be tangent because we get here, let me change my color. As I look at this, what are these slopes? Slope equals undefined, looks like, right? So that could be an asymptote, or it just could be so big it looks vertical. So, if we're talking about cube, the cube grows pretty darn quickly. And as we move farther and farther out, maybe this is the computer doing the best it can at drawing a line that, let's say, is some massive, huge number, but it's not quite vertical. So it could be argued either way. They would have to do a nice job of choosing multiple choice answers if you're doing a matching. You couldn't do tangent and cubed in the same situation. It is just, they're too close. All right, give it a whirl. Pause, give it a try. Actually, you know what? I'm going to encourage you to do this. Make a sketch of each one of these functions underneath them, and then try to compare it back to the slope field. All right, let's see how you did. Hopefully, you can make a sketch at least of this first one. This first one's going to be a parabola, right? It's going to be something like that. All right, e to the x. Oh, come on. E to the x starts low and grows high. It looks like this. E to the negative x, that's the same function, except it's 1 over. So this is the same as 1 over e to the x, which is just going to be a decay. It's the same graph, except it decays instead of grows. Sine and cosine, we already talked about those. It looks something like this. Natural log, it's the same as e to the, except instead of growing up and out, it grows sideways. So that one looks something like that. Probably should draw some coordinate. Okay, now if we go back to our slope field and try to draw a particular solution, I would say it looks something like that, I guess, which clearly is closest to E. So we're going to choose E as our best fit. Match the slope field with the different equations. So now we've got 6 slope fields and 6 differential equations. And you need to match one with one. So I go through first and I try to figure out if I can do it graphically. And then after that, I try to plug in some points. For me, those are the 2 easiest ways. So if I look at example A, could you make a pretty good sketch of that function? I would say yes. Horizontal, then goes like this. Horizontal, then goes like this. That's got to be a parabola. So do we have a parabola option? We do not. So now what? Oh, yeah, this is the original. So this is a differential equation. So which differential equation would look like a parabola when you integrated it? We'd have to integrate these. We'd have to solve each one of these. All right, so maybe that didn't click. Maybe that's not the best way to explain it. Let me try the other method that I use. What I do is I pick a point and I plug it in to see if it actually works. So like, let's take 0, 0. That's the easiest one first. So 0, 0. E to the 0 is 1. No. When I put a 0 in for x, I would get a y. I wouldn't even have a y, but it would be equal to 1, not 0. I picked this point 0, 0 because it had a horizontal tangent line, so the slope would have to be 0. The answer should be 0. When I go 0 over 0, that's still not 0. That's undefined. 2 minus 0, that's 2, not 0. Plug in, ooh, that one works. 0 minus 0 works. And sine of 0 is 0. So right now, all 3 of these works. So let's try with the one right above it. That's 0, 1. So I put in 0 for x. Yes, that's 0. I put in 0 and 1. That's not. I put in 0. I get 1 again. Nope. So those are all eliminated. This has got to be number 4. So I did it by guess and check. I started to pick points on the curve that were easy to tell what their derivative was, and I made sure that they fit in the differential equation. So let's try it again. This one. So I'm going to pick these points right here. These are the points that I'm going to highlight. And I'm going to see which equation I can now eliminate 4. Can't work again. Because, yeah, none of these match. None of these repeat, I should say. Okay, this is the point 0, 2. When I plug 0 for x and 2 for y, I should get an answer of 0. So e to the 0, nope, that's not it. 0 over 2, nope, that's not it. 2 minus 2, yep, that works. 0 minus 2 is not 0. And then sine of 0 is 1, so that one's easy. That point, 0, 2, had an answer of 0. So when I plugged in, let me actually write the points out. I plugged in 0, 2, and I need to get a 0 out. Going back to this one, I plugged in 0, 0, and I needed to get a 0 out. That wasn't enough information, so then I plugged in 0, 1, and I still needed to get a 0 out. Because at 0, 1, the slope of the tangent line in the slope field is still 0. Hopefully that's making sense. If not, we can talk in class. Nope. I'm going to save that one for last, and hopefully that'll be the one that I don't have to figure too much about. Oh, I can eliminate. I didn't cross out 3. All right, here I go again. I'm going to use all of these slopes, all these points, because all these slopes are 0. So the first one I'm going to pick is 0, 0. So when I plug in 0, I better get a slope of 0. E to the 0 is 1, no. 0 over 0 is undefined, no. Those are gone, those are gone. 0 minus 0 is 0, and sine of 0 is 0. So both of those are still alive. Now I'm going to pick 0, 1. You're going to see the same argument that we had before. When I do sine of 0 now, I get 1, not 0. Wait. Yeah, I could have killed that here. Sine of 0 wouldn't be, that's gone already. I don't know what I was talking about. I didn't need to check another one. It's got to be V. V. Wait. Yeah, wait, no. Sine of 0 is still 0. But 0 minus 1, okay, this one gets eliminated. My bad. 0 minus 0 is 0. 0 minus 1 is negative 1, which is not 0. So that one's out. So it's got to be this. And yeah, that makes sense. I don't know why I did this by points. This clearly looks like a trig function. If I did a particular solution, it would look something like that. Look something like that. Yeah, that's for sure some sort of trig function. So I want to highlight, I want to find a point that is easy to figure out its slope. 0, 0 again. 0, 0 needs to be 0 when I plug it in. E to the 0, nope. 0 over 0, undefined, nope. So that's got to be this, 0, 0. Let's just double check one more. So at the point 1, 1, the slope needs to be 0. 1 minus 1, yep, that has a slope of 0. So this is 5. E to the x, I could do that one graphically. I don't even need to. This for sure is a function. If I try to do a particular solution, looks something like that, which is the sketch of e to the. And then why is it that, I guess I kind of cheated there. This is the graph of e to the x. The derivative is also e to the x, right? It's going to be the same thing. You could plug in. Anyway. All right, to try to explain this last one, I'll do my best. I know it's got to be 2 by process of elimination, but let me try to teach why. Okay, so look at all these slopes. Look at all these slopes. Then look at these curves. Does that look familiar back to our conic section days? Actually, I don't know if that helps you or not. This is how Corpy explained it. We got to know our conic sections pretty well to do that. But that's a hyperbola. I don't know if you remember those from our conics, but that's a hyperbola. Okay, let's do one more in this section, and then we'll pause and come back to the rest. Match the slope fields with the differential. Okay, so you try it this time. I'm going to encourage you to pause and try to come back. Okay, let's see how you did. So I'm going to look for anything that has slope of 0. Those are usually the easiest to find out. So I'm going to use the point 1, negative 1. 1, negative 1, when I plug that in, needs to come out to be 0. So when I plug in 1, half of that is 1, 1 minus 1. Yeah, that works. Half of 1, no, that doesn't work. Negative, no, that doesn't work. 1, negative 1, okay, so I'm down to 1 and 4. So let's try another point. Let's try the point negative 1, 1. Needs to come out to be 0. So when I plug negative 1 in for x, I get half of that. Wait. I'm way wrong. 1, I'm already done with this one. I plug 1 in there, that's half. Half minus 1 is negative half, it's not 0. So that's got to be 4. This one's got to be 4. I'll put it underneath. I'll put it on the side, I guess. That one's got to be 4. And I can now eliminate 4 from because none of these repeat. All right, the slopes here are all 0. Now, what do you notice all these slopes have? They all have the same x value of 2. So whatever I plug in for x, when I plug in 2 for x, it always has to give me an answer of 0. Plug in 2 for x, yeah, half of 2 is 1, 1 minus 1 is 0. Plug in 2, that's 1. Plug in 2 over anything is not going to be, and then 2 plus anything doesn't always end up being 0, so this has to be 1. I don't know why I wrote it up there. So all of these have slopes of 0, so 0, 0. Well, actually, I don't know if that actually hits at 0, 0, do I? So this is 0, 1. This is y is some 0. This is x is some. This is the point 0, 1. So when I put 0 over 1, I get 0. Yep. What says 0, 2? When I put 0 over 2, I get 0. And then when I put 1, 2, 3, that's not always going to be 0. So yeah, this is definitely 3. And then finally, this has got to be 2. Let's see if we can figure out a good spot y. So all of these points, all of these have a y value of 2. And they end up having a slope of 1. And so when I put 2 into this, half of 2 is always 1. All right, I'm encouraging you, if you aren't going to watch the second video right now, to dive into the homework and see if you can get some of that sucker done.